Calculating carrier concentration.
Yes. Okay, so today's lecture, we started calculating carrier concentrations. We got into the idea of extrinsic doped semiconductors last time and energy bands, and today we're going to talk about carrier concentrations, and we're also going to talk about the Fermi function, density of states, and come up with formulas on how to calculate the electron and hole concentrations in a semiconductor. So the way that we're going to do that is just by following this, I think, an intuitive, statistical type approach. And what I mentioned at the end of class last time is that this is similar to the Costco parking lot analogy. So we're going to calculate carrier concentrations, which means we're going to calculate the concentration of electrons in a semiconductor. We're going to calculate the concentration of holes in a semiconductor. This is important, of course, because holes and electrons are the things that make a semiconductor conductive. So to figure out what the concentration of electrons or holes are, the parking lot analogy is that you're looking for the concentration of cars in a parking lot, in a Costco parking lot. Okay, so the first thing you want to look at is the concentration of parking spaces. Okay, so how many parking spaces do you have per square meter? Okay, that's the density of states, the density of spaces that you have. And the Fermi-Dirac distribution is the probability of finding a carrier in each of those energy states. So the analogy of that would be, what is the likelihood that a parking spot is full? So if you were to take the density of parking spaces, so the number of parking spaces per square meter, and you multiply that by the probability that the parking space is filled, what are the units that you would get? So let's say, again, I'll repeat it again. The density of parking spaces is the parking spaces per square meter, right? And then you multiply that by the probability that the parking space is full. So what are you going to get if you multiply those two things together?
Number of parking spaces by meter square.
The number of cars per square meter.
Number of cars per square meter. That's right.
There's no unit.
That's right. That's right. That's right. So the parking lot analogy goes something like this. Number of parking spaces per meter squared. Multiply this by probability that space is full or occupied. Let's say occupied. So the units here, is 1 over meter squared. You're multiplying this by something that's unitless, and so you get the units is 1 per meter squared. So what you're going to get here is the number of cars per meter squared. In other words, the concentration of cars. All right, let's just make this larger. Right, the parking lot analogy is like you have what's called the density of parking spaces, the number of parking spaces you have per meter squared, The units for that is 1 over meter squared. You multiply that by the probability that the space is occupied by a car, and a probability is unitless, right? And that will give you, the units will be 1 over meter squared, or it would be cars per meter squared. So this will give you the number of cars per meter squared. In other words, the concentration of cars. Okay. So similarly, we can look at the number of states per centimeter cubed. Multiply that by the probability that the state is occupied by an electron. All right, so let's put down our units here. The units here is 1 over centimeter cubed. Probability is unitless. All right, so can someone tell me then what does the product of these two tell us, and what are the units?
Number of electrons per centimeter.
Right. The density, or we can call this the electron concentration. And the units here is 1 over centimeter cubed. Just make this larger so everyone can see my messy handwriting. So in a semiconductor, you have the number of states. When we're talking about the number of states, we're talking about quantum states. Remember, solutions to the Schrodinger equation give you the different energy states an electron can be. So this is the number of states per centimeter cubed. Multiply that by the probability that the state is occupied by an electron, and that gives you the electron concentration. Number of electrons per centimeter cubed. So if you know the electron concentration, you also know the hole concentration. But I'll get to that later. All right, so this first part here, the number of states per centimeter cubed is the density of states. The probability that the state is occupied by an electron is the Fermi-Dirac distribution. All right, that's why we have to consider both of these things. So let's get into the Fermi-Dirac distribution first. If you read about like statistical mechanics, it's kind of an interesting area. I was reading about it recently. It's a bit of a new area for me, but there's 3 different types of distributions. There's one distribution called the Boltzmann distribution, which governs things like gas molecules. Distributions, by the way, is like you have a system where you have a whole bunch of particles, right? And you're trying to understand the continuum behavior of the particles as a whole. Like you're not trying to track each individual particle, but if you just have a ton of those particles, you're trying to look at the aggregate behavior of all the particles as a whole. So that, in a nutshell, is what statistical mechanics is about. One type of statistical mechanics, which is called Boltzmann statistics, and that an example of that is used for gas molecules. You have tons of gas molecules in the air. They have an aggregate behavior, like the pressure that they exert on the walls of a container. PV equals nRT. Yeah, exactly. Those are all like aggregate behaviors resulting from the aggregate behaviors of a distribution of particles. Another example is, I think that it's called the Bose-Einstein distribution, and that governs like black body radiation and things like that. Then there's the Fermi-Dirac distribution, which governs the behavior of electrons in a 3-dimensional lattice. And we're not going to derive this, but basically from this distribution, there's kind of 2 pieces of intuition, okay? Number 1 is that the electrons are not indistinguishable from one another. And number 2 is that two electrons cannot occupy the same energy state. There's a third thing also that the lower energy states gets filled up first. So the Fermi-Dirac distribution, without getting into the derivation of it, it has to do with how electrons fill up the energy states that are available to them. And the very simple one-sentence description you could have of this Fermi-Dirac distribution is that electrons are more likely to be in the lower energy state. They are less likely to be in high energy states. And this is really a mathematical description of that statement. Qualitatively, we are likely to find electrons at energy states below the Fermi level, and we're less likely to find them at energy states above the Fermi level. So if we make the statement that electrons are most likely to be in a low energy state, that means the low energy states are filled, right? And the high energy states are all empty. So there should be something in the middle where the probability is 50%, right? Because the Fermi function is saying at low energy states, the probability of finding an electron at a low energy state is 100%. It's full. The lower the energy state is, the more likely it is it'll be full. So very low energy states, 100% probability. At high energy states, really, really high energy states, there's a very, very low likelihood. So the probability there is 0. There should be something in the middle, right? There should be some energy at which the probability of finding an electron is 50%. That energy is the Fermi level. Right? And I just answered this question here. But you can do the math for that. So the Fermi level is an energy at which the probability of finding an electron is 50%. The actual function looks something like this. And again, we're not deriving this, so just take this as a law. This is the function. Probability of finding an electron is equal to the Fermi function. It's a function of E, and it's equal to 1 over this exponential function on the denominator. 1 plus e to the e minus ef over kt. That's the probability of finding an electron. And intuitively, this should make complete sense. The probability of finding a hole is 1 minus the probability of finding an electron. Why is that?
There's no car in that space.
What's that?
There's no car in that space.
There's no car in that space, exactly. Either a state is an electron, either it's occupied by an electron, or it's not occupied by an electron, in which case it's an empty state. Right? So the probability of a hole is basically the converse of the probability of finding an electron, or 1 minus the probability of finding an electron. So this K is the Boltzmann constant, the T is the temperature, and the product of these two is usually equal to, depending on what units you use, it's 0.026 millivolt Kelvin. We'll talk about that more as we go. This is what the Fermi function looks like. And I want you guys to mathematically understand why it looks like this. So at low energy, so this is energy on the x-axis here, and then the Fermi function on the y-axis. First of all, notice that the Fermi function, it's maximum at 1, and then the lowest value is 0. It's a probability, so it has to be between 0 and 1. As I mentioned earlier, at the Fermi level, at EF, that's the Fermi level, the probability is 1/2. So that's why you have this dotted line here. And the thing about this function, about the mathematics of this formula, is that it is a transition from 1 to 0. This mathematical formula represents a transition from 1 to 0 as you go to increasing energies. So the way you can think about this is that look at this term here. It's E minus EF over KT. So let's say the energy is really small. All right, so what happens to this E minus EF term? when E is very small?
So large negative.
It's a negative number, right? It's a large negative number, right? And so what happens when you take the exponential of a large negative number?
It'll be the reciprocal.
It's a reciprocal, right? So the exponential of a large negative number, it goes towards 0. So you end up with 1 over 1 plus 0, which is basically just 1. Okay. Now, when E is very large, what happens? Suppose this E is very large. Now what happens to this exponential term?
Goes negative.
Goes larger, right? So it becomes very large compared to the 1 next to it. So now you have a situation where it's 1 over, well, this becomes negligible. It just becomes 1 over a very large number, right? And that is basically 0, right? So this function nicely describes the transition between 1 and 0. You also see that there's a temperature dependence. And the cool thing about the Fermi function is that the rate of transition, it depends on the temperature. All right. If you have a a very low temperature, in the lowest case is 0 Kelvin, the Fermi function looks like this. It's a sharp transition. Now keep in mind, if t is equal to 0, then this is mathematically invalid, right? Because you have a 0 in the denominator. So when t is actually equal to 0, you won't be able to solve this formula mathematically. But if you take the limit as t goes to 0, then you'll find that as you go to 0, the Fermi function starts looking more and more like a backward step function. As you go to higher temperatures, the transition from 1 to 0 becomes more gradual. Okay? This is because this E minus EF, it's the difference here divided by this KT. So the higher T is, the larger this value has to be in order for this to drop down to 0. So it becomes a more gradual change. This, by increasing T, you're decreasing the rate constant, the rate at which it transitions to 0. All right, so this is a mathematical function, the Fermi function, and it nicely describes the probability of finding an electron at EF. So when you're below EF, the probability is very high. As you go above EF, the probability of finding an electron at the state transitions to 0. Lower energy states are very likely to be occupied. High energy states are less likely to be occupied. So that's the Fermi function. You'll have some problems in your homework where you deal with this. And one little hint there is that a lot of times when we do energy band diagrams, we get the energy band, the units for energy band diagrams is given in electron volts. We generally do not use joules for energy band diagrams. The electron volts and joules are both units of energy. And there's a conversion that you remember that one electron volt is equal to 1.6 times 10 to the negative 19 joules. I'll just note it again here just so you have it. It's in your notes, but 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. All right? So this Boltzmann constant can be given in terms of joules per Kelvin, but you can also convert this joules into electron volts, and so you also have a version of the Boltzmann constant, which is electron volts per Kelvin. 8.63 times 10 to the negative 5 electron volts per Kelvin. All right, any questions about the Fermi-Dirac distribution? All right. Now, how do we tie this into our discussion of doped and undoped semiconductors? We'll talk about that. So we're visualizing the Fermi distribution and the Fermi level. So the closer the Fermi level is to the conduction band, the more electrons there will be in the conduction band, and this is the N-type semiconductor. The closer the Fermi level is to the valence band, the more holes there will be in the valence band, and this is the case with a P-type semiconductor. In an intrinsic semiconductor, the Fermi level is in between, midway between EC and EV. All right, so let's start off with the intrinsic semiconductor. We'll take a close look at that here. Zoom in on that. All right. So, these might be a little bit hard. Well, okay, enlarge it. It should be a little bit easier to see then. What this plot is showing is it's showing this energy band diagram, showing the carriers as well in this portion here. You have your EC and your EV. Remember that in an intrinsic semiconductor, you can have, this band is mostly full, this band is mostly empty. But if you can generate electron hole pairs. How do you generate electron hole pairs? What are some ways you can do that? The way that we talked about.
Temperature.
Increase the temperature, right. There's another way you can generate electron hole pairs too, which we may not have talked about in class, but maybe someone can guess.
Induce a voltage?
Yes, there are ways to do it by high fields.
Projecting light.
Projecting light, yeah, exactly. If you put radiation in there, that you remember how E equals HF. So if you put high energy radiation, you can actually cause an electron to go from the low energy to high energy state. So those are a few ways you can get the electrons to go up here, but they're created in pairs. So what we're showing here is the Fermi function and the Fermi level. In an intrinsic semiconductor, as I mentioned, the Fermi level is right in between EC and EV. So what this is showing here, it's showing you the Fermi function with the blue line here, okay? And so what's being shown is this is energy on the x-axis, and the Fermi function, or the energy is going up and down, and the Fermi function is going left and right here. So we basically took the graph from the last slide and we rotated it counterclockwise 90 degrees. So the Fermi function here is 1, the Fermi function here is 0. The probability of finding an electron transitions from 1 to 0 as you increase the energy. So the electrons are more likely to be below the Fermi level, less likely to be above. Let me say that more clearly. The electrons are very likely to be at states below the Fermi level. They're less likely to be at states above the Fermi level. So the Fermi function describes that probability. So in the intrinsic case, you have a high probability down in the valence band, so that most of the valence band states are full. By the time you get in between the valence and the conduction band, you're at EF. The probability of finding an electron in a state at halfway is 50%. But keep in mind that there's no states there. The Fermi function just doesn't tell us about how many states there are. It only tells us the probability of finding an electron if there was a state there. Okay, very important point. Because as we talked about before, in a semiconductor, there's a band gap where there are no allowable states. By the time we get to the conduction band, we are now significantly above the Fermi level, so the probability of finding an electron there is very close to 0. And that's what this zoomed in section shows. It shows that the Fermi function is very close to 0. The Fermi function at the EV is very close to 1. The Fermi function is at the conduction band is very close to 0. Notice I said very close, not equal to. The fact that the Fermi function is very close to 0, it's not 0. So that means there are states up here in the conduction band, and there's a very small but non-zero probability that those states are filled. That's why you can have electrons there, but there just are not that many. Very, very low concentration of electrons. So now we look at the N-type semiconductor. The difference that you notice here is that the Fermi level is now close to the conduction band. The Fermi level has shifted upwards from in between here to close to the conduction band. So what that means is if we compare these two, before there was a very, very low probability of finding an electron at EC. Now there's a larger probability of finding an electron at EC. Because the Fermi level shifted higher, now since EF is closer to EC, the probability of finding the Fermi function, the Fermi probability, is slightly higher now in the n-type case compared to the intrinsic case. All right. So as a result, you have more electrons in the conduction band, and conversely, your Fermi level is farther away from EV. So before there was a probability that was very close to 1, and here the probability is even closer to 1. So there's very few states. There ends up being these states end up being mostly full, even more so than before. There are still some holes there, but very few and far between. So just to remind you, another difference between the n-type and intrinsic semiconductors is that in the intrinsic, there's an equal number of electrons and holes. In this drawing here, you can see 4 electrons, 4 holes. In the n-type semiconductor, the number of electrons and holes are not equal to each other. So you can see 1, 2, 3, 4, 5, 6, 7 electrons here and only 2 holes. Does anyone remember why they're not equal to each other? The donor, right? Every donor that you put in, you created 1 extra electron in the lattice. Exactly. All right. So, yes.
Can you dope something from like the 6th column so there's 2 extra electrons? Like if you combine 3 and 6?
The question was, can you use something from column 6 to create a semiconductor?
You have more than 1 donor per donor atom.
You can create something, the 2,6 semiconductors where you combine a column 6 element with a column 2 element. Well, those combine to make an intrinsic semiconductor. If you combine them in equal ratios, then they combine to form an intrinsic, right? Mm-hmm. But so your question is more like, if you took a column 6 element instead of a column 5 element and dope that, would you actually create 2 extra electrons in the lattice? Mm-hmm. And the answer is I haven't seen that. It's not done in standard practice as far as I know. There's usually column 5, and I can there are probably examples out there. I'm just not familiar with it. But when you take a 6 electron atom and you put it into a space where there's originally was supposed to be 4, maybe it works with column 5, but it doesn't work so well with column 6 because you have extra electrons, extra energy states, and like the 6, the extra 2 electrons also result in extra 2 protons. And so that will create a different boundary condition for the Schrodinger equation, so the solutions to that may change. So when you put a new atom in, there's a lot of things you have to consider. You have to consider the size of the atom, you have to consider how many protons there are, you have to consider how it interacts with the neighboring atoms and whether it will form the bonds, the tetrahedral bonds that are typical of this kind of lattice. So
So it's probably safe to say it's just 1 donor electron?
It's typically a column 5 element with 1 donor electron, yeah.
Okay, fair
Mm-hmm. Certainly it's the case with silicon. So with p-type is, you have a Fermi level here. It's just closer to the valence band. Since it's farther away from the conduction band, the Fermi probability becomes very, very close to 0. So there's very few electrons. But by moving the Fermi level closer to the valence band, the probability of finding a hole increases. Right? So the way you can think about this, basically, the Fermi level in the middle, it's like equal probability of holes and electrons. As you move the Fermi level up, electron concentration increases, electrons in the conduction band increases, holes in the valence band decreases. Vice versa, you shift the Fermi level close to the valence band, you get more holes in the valence band, fewer electrons in the conduction band. So this makes for a very nice way to do calculations and predict the behavior of the material. So quick question on the Fermi level: which of these acts as a metal, insulator, and semiconductor? The way I want you to think about this is what the definition of the Fermi level is. So let's give a second to think about it, and then we'll then we'll talk about it. So take a look at these three materials and see what you come up with. So if you have to select, one of these materials we're going to say is a semiconductor, one is an insulator, and one is a metal, meaning a conductor. So let's start with material one.
Semiconductor. Semiconductor.
It's a semiconductor. Okay. It's I heard one was semiconductor, and what was the other one?
Conductor.
One is conductor. Okay. Okay. So let's talk about those. So let's see what the arguments are. Like, let's start off with what are the arguments for this being a conductor?
Closer to the conduction band.
Okay, it's close to the conduction band. Okay. So if the Fermi level is, so your argument is if the Fermi level is close to the conduction band, then there should be some electrons in the conduction band.
The probability is going to be higher.
The probability is going to be higher. Right, so since the Fermi level is close to, we don't have the conduction band and valence band labeled here, but there's band 3 and band 2. If the Fermi level is fairly close to band 3 and band 2, that means there could be electrons in the conduction band, and there could be holes in the valence band, in the band 2.
Is
All right.
band 1 the valence band? Or do we not?
No, yeah. I shouldn't even be saying valence and conduction band, because the purpose of this question is to keep it completely abstract, so you're just thinking about the Fermi level. So if the Fermi level it's in between these two bands, but it's relatively close to both of them. That means that band 2, okay, let's start with band 1. Band 1 is very far below the Fermi level. So what does that mean? Is it going to be full or empty?
It's going to be 100%.
It's going to be most likely 100% full, because it's so far below the Fermi level. You go to band 2. The bottom of band 2 is going to be mostly full, but as you get to the top of band 2, as you get to the top of band 2, notice that it's pretty close to the Fermi level. So that means if it's slightly below the Fermi level, there's a chance that some of those states may be empty. So some of these states at the top of band 2 may be empty, and so that means the band 2 could become conductive. And as you go above the Fermi level in band 3, it's all the way up here, of course, the states are going to be completely empty. But once you get closer to the Fermi level, some of those states may not be empty, because the distance between here and here, qualitatively, is small. All right. So before calling this a semiconductor, let's just compare it to the second material. Let's start with band 1 here. Band 1 is very far below the Fermi level, so completely full, not non-conductive. This band 1 is. Band 2, the Fermi level is smack dab right in between the middle of band 2. So what does that mean?
It's a conductor. It's not.
Okay, it's a conductor, but let's back up for a second. Like, what does it mean about the band specifically?
It's got electrons and holes really close to each other.
Yeah, that means that these states below EF are there's a lot of electrons below EF, but most of the stuff above EF is empty. Very close to EF, there's a transition zone, right? The Fermi function transitions from 1 to 0 as you go through EF. But there's a bunch of empty states here, and there's a bunch of full states here, and there's this transition zone here. So this band has a lot of electrons and has a lot of empty states. All right. When a single band has both carriers and empty states, it makes it a very good conductor. Right. Band 3 being very far above the Fermi level, that's going to be non-conductive. Right. So in this material too is certainly a conductor, and band 2 is the one that's responsible for all the conduction. Now material 3 is similar to material 1 in some sense, because you have EF that's not within the band, you have it in between two of the bands. All right, the difference between material 1 and material 3, similar to a question that we had at the beginning of this chapter, is that the distances are just larger. All right, so when the distances are larger, what does that mean?
More insulated.
It behaves more like an insulator. That's correct. Band 3 is going to be mostly empty. Band 2, since it's far away from EF, compared to material 1. So if we compare material 1 and material 3 together, here you have EF, and the band 3 and band 2 are fairly close to it. Here you have band 2 and band 1, which are quite far from EF. So the farther something is from EF, the higher above it, the less likely there is of finding an electron, and the farther you go below it, the less likelihood there of finding a hole. So this material would have less carriers than material 1. So material 3 has more like insulator-like properties, and material 1 has, in comparison, more semiconductor-like properties. Any questions about that? Good. All right, so now that we talked about the Fermi-Dirac distribution, now we can talk about the number of available states, the density of states. So again, just like finding the concentration of parking spaces per meter squared, I don't know if that helps visualize things or not, but it's similarly, there are parking spaces for electrons. Those parking spaces are the quantum states that we solved in the Schrödinger equation. Those are the energy states that an electron can reside in, and there's a set of discrete states that not discrete states. That's a single atom. There's a band of states that the electron can reside in. In a solid material, there's a band of energy states. All right, but there's a concentration associated with that too. The more atoms you have, the more states there will be, the more orbitals there will be for the electrons to reside in. All right, if you think about this in terms of the atomic picture, the electrons are residing in those sp3 hybrid orbitals, right? If they're in the valence band, that means they're residing in one of those sp3 hybrid orbitals. If it's in the conduction band, what does it mean if it's in the conduction band? Does anyone remember? So when we're talking about these energy band diagrams, an electron in the valence band, that means if the electron is in the valence band, that means it's bound in a covalent bond. It's one of those sp3, it's in one of those sp3 hybrid orbitals that connects the silicon atoms together. If an electron is in the conduction band, what does that mean physically?
So outside of the lattice.
It's loosely bound to the lattice. It's still part of the lattice, but it's loosely bound. It can move around. If an electron is completely free from the lattice, means it's away from the material, that means it's reached what's called the vacuum level, E0. We haven't really spent much time talking about that yet. And that has to do with the photoelectric effect. Actually, we did mention photoelectric effect in module 0. But anyway, getting back to this then. So there are energy states, right? An electron can be in this conduction band states, valence band states, but there are densities of states in each one of those energy bands. And this is also something that is derived from statistical mechanics, and we are not going to go into the details of that in this class. But what you need to know for this class is that the density of states tells us the number of available energy states in a semiconductor volume within a range of energies, and that's denoted by n of E. All right, n is density, E, so n is a function of density, n of E, dE. And then qualitatively, in a three-dimensional material, this function, n of E, is a square root function. Oops. So as you increase the energy, the density of states increases like as a square root function. All right, and the way it plays out in a semiconductor, I think that this is the intuitive thing that you want to remember. We have our energy band diagram here, okay? Our EC and EV. Just to remind everyone, there are no energy states between EC and EV in an intrinsic semiconductor. That's the band gap. But there's a bunch of energy states up here and a bunch of energy states up here, or down here, below EV. What this is saying is like, what is the actual density of states? The density is actually not constant. If we look at EC, for example, it turns out that the density of states increases as you go to higher energies. So the way that you can kind of think about that is, you remember how before we were drawing energy states as lines? So we could say that there's a low density of states here, but as you go higher, there's a higher, the density of states increases as you go to higher energies. Does that make sense? So there are energy states near the conduction band, but there's the density of those states. The concentration of those states is lower near the conduction band, and it increases the higher you go up.
Is there like a top edge to that band?
Yeah, there is. Oh, absolutely. Yeah, the conduction band is a band that looks like this. It's a continuous set of energies. Yeah, good question. But the reason we do it in this shorthand, because we are really interested with semiconductors. We're really interested in what's happening between the band gap, like at electrons near conduction band and holes near the valence band. That's why we don't bother drawing all this stuff above here and all this stuff below here. So the point I'm trying to make here is that there's a low density of states. So it turns out the density of states actually goes to 0 right at the conduction band. But as you increase, the density of states increases. So what's being shown here is this is the energy, and this is the density of states. So this axis here is 0 here. So there's technically is 0 states right at the conduction band, but as you go to larger energies just above the conduction band, the density of states increases like this as you go up. And it increases as a square root function. So similarly in the valence band, the density of states here also increases as a square root function. Right? And remember here that the density of states goes down to 0 at EC, it goes down to 0 at EV, and it stays 0 in between the two, because in the band gap there are no available energy states. So going back to the parking lot analogy, if I told you, a simple problem would be if I said the density of parking spaces was a constant. Let's say there's, let's say there's like 0.1 parking spaces per square meter, or 0.2 parking spaces per square meter in a Costco parking lot. Right? I'm just making up a number, right? But let's say it's a constant. You multiply it by the probability that the parking space is full, and it's just a product of just two numbers, right? Now what if I tell you that, there's actually, this parking lot is more complicated. There's trees in some places. So this part of the parking lot has a low density of parking spaces, and this part here has a very high density of parking spaces because it doesn't have trees. It's just all concrete, right? Now if there's different densities of parking spaces in the parking lot, you can't just do a simple product, right? You have to do an integration. So the proper way to find the electron concentration would be to take into account that you have a varying density of states, and then you have a varying Fermi function. You take the product of the two functions and you integrate over an energy range. Engineers often like to find shortcuts, partly because we're lazy, but also more importantly is that doing things by hand gives you more intuition. Right? That's why we often try to take shortcuts that allow us to do calculations and things by hand to give us an intuition. And the simplification that engineers do here is that they take an effective density of states. So parking lot analogy again, you say this part of the parking lot, half of the parking lot has has trees in it, so it has a low density of parking spaces. This other part, which is completely concrete, has a very high density of parking spaces. So why not, if we're just trying to come up with a composite number, you could just say, what's the average of those two, right? You just kind of average those two out, and then you have one number that can be multiplied by the probability that the space is full. So similarly, what you do is you kind of take this, the effective density of states, you can think about it as being kind of like an average density of states in the valence band and an average density of states in the conduction band. All right, it takes into account this square root function. So we're not going to derive where this equation came from. I just want you to know it and know how to use it. And in fact, NC and NV, you may not end up, for basic calculations, you often don't even end up seeing a lot of these numbers. We end up just using this other constant called Ni, which we'll talk about later. But these constants are used to derive Ni. That's why we bring it up here. So these formulas, this is Nc is the effective density of states in the conduction band, and V is the effective density states in the valence band. And so you see this is number 2 here. This is all constants. This Mn star is the what's called the effective mass, the density of states effective mass of the electron. We'll talk about density of states at the end of this module. So just take this as a constant for now. The kT you've seen before in the Fermi function, and then this is Planck's constant at the bottom. All right, and this is similar for the valence band, except you have this whole density of states, and then you have this 3/2 function. So now, like calculating electron concentration. So again, hammering this to death. To find the concentration of electrons, you multiply the effective density of states multiplied by the probability that the state is full. So this N0 is what we call the electron concentration, the concentration of electrons in the conduction band. This is N, and then this is f of E is a Fermi function. So if we're looking at the conduction band, the N0 is equal to the effective density of states in the conduction band, N sub C, multiplied by the Fermi function. And that's equal to this. Nc divided by this quantity. This is just coming from the Fermi function. All right, and it simplifies to just Nc e to the negative Ec minus Ef over Kt. How did this simplify? It looks like this one term went away. Why did this one term go away? Yeah, because Ec minus Ef is large. Ec is above Ef, right? So this exponential term quickly becomes much larger than 1, so you can ignore the 1. So similarly at the valence band, the whole concentration is equal to Nv, the effective density of states in the valence band, times the Fermi function in the valence band. And again, something that one term. Now, something different that you have in the Fermi function is you have Ef minus Ev. The reason you have Ef minus Ev is because this has to do with when you're finding the whole concentration instead of the electron concentration. It's whole concentration is 1 minus the electron concentration. So that's why we're not going through all the steps here, but that's how this kind of comes about. Ef minus Ev, whereas here it was Ec minus Ef. So the Fermi level was the second term here, and here it's the first term. So Nv e to the Ef minus Ev over Kt, this one term goes away again. All right, so those are the formulas for calculating the electron and hole concentration. Most of the time you won't even be using these formulas. You won't be, as I mentioned, you won't be using Nc and Nv so frequently. We'll get to that in a second. This is a qualitative look at the carrier concentrations in N, P, and intrinsic semiconductors. So what we're doing here is we're taking into account the density of states and the Fermi function, and this is not formulaic. This is purely conceptual, but it's important that you understand this as well. We'll start with the intrinsic semiconductor. So this is your energy band diagram here on the left. This is the density of states here, second one, and the Fermi function here, and then the electron and hole concentration here. So starting from the left here, I mentioned before, the density of states increases the farther you go away, farther you go above EC, the density of states increases. Below EV, the density of states increases. The Fermi function looks like this. Fermi function drops to 0 above EF, and it goes to 1 below EF. Now, what the purpose of these plots is so you can visually see when you multiply these two functions together. The density of states is very close to 0, and it is 0 within the band gap, but it increases as you go to higher energies, and the Fermi function drops as you go to higher energies. So if you multiply these two functions together, remember, to get the electron concentration, you have to multiply those two together. You get a small region here just above EC where there's electrons. All right, way up here where this hand is, there's a lot of states, but the probability that those states are very likely to be empty. Below the conduction band, there's a very higher probability of finding an electron, but there are no states. So that's why this little blue zone is kind of like the Goldilocks zone, is where you can find, just above EC is where you'll find most of the electrons. And similarly for holes, you can do the same kind of argument for holes. So if you compare this situation to an N-type semiconductor where the Fermi level has been shifted up, the distributions of electrons and holes changes. Because you've shifted the Fermi function up, now you have a larger region of energies where there can be an electron, and so this function, so you have a larger electron concentration and a smaller hole concentration, and then vice versa for the p-type. So in the p-type, the Fermi levels have shifted downwards, so you have a lot of holes and fewer electrons. So the purpose of these plots is to show you that the conductive electrons lie very close to the conduction band, and the conductive holes lie very close to the valence band. And that's the reason why when we draw energy band diagrams, we don't draw the entire band, we just draw we're interested in what's happening near EC and near EV. All right, questions then? All right, so there's a situation where we can have multiple dopants. All right, this is if you let's say you doped your silicon with a column 5 element and you dope it with a column 3 element, both. So every time you put in a column 5 element, how many electrons are you putting in the lattice? How many additional electrons?
1.
Exactly 1. For every atom that you put in, you assume that electron gets ionized and that it can move around the lattice. You get 1 electron per atom. Now, what if you were to take that 1 electron, that arsenic, that 1 extra electron, right near it, there was like a boron. A boron which is an acceptor, so it has an incomplete bond, it has a hole. What do you think is going to happen to that electron? It's just going to fill that hole. It's a low energy state, and everything's happy. So now you can essentially neutralize the material by adding a p-type dopant to it. Let's say you started off n-type, right? If you want to kind of erase what you did, you can put a p-type dopant in there, and now you'll have like a neutral material again. You'll move that Fermi level back down to the middle.
But this is if the acceptors and the donors have the same numbers of atoms in the
if you have the exact same number. Right, exactly. Now, a couple caveats here, right? Obviously, if you doped it with arsenic and then you doped it with boron, you don't have the same material that you started off with, right? You still have these dopant ions, right? That can change the properties of the material also. But if we're just talking about carrier concentrations, then it's a way to quote-unquote erase. And actually, this type of thing is often done in semiconductors. I don't know if you all remember. We can. I'm just going to draw this out. We're obviously going to talk about this a lot more later. But one particular applications of multiple dopants is like, let's say you start off with a p-type semiconductor, a block of p-type semiconductor, and you want to create a diode. So one of the ways you can create a diode is, this can be one end of it, and then you dope this n-type. You can create an n-type material here and put a contact here, right? You made a diode. The way they actually do this is that they start off with a block of p-type material that's been doped with boron, and then just the top of it you dope with a much higher concentration of phosphorus, column 5 element. And you can actually switch if you add enough phosphorus, you can make it neutral. And if you add even more phosphorus, now you've changed it from p-type to n-type. That's the way they actually do it in practice. Because you can't just take an n-type and a p-type material, put it together, and expect to make a good quality diode. Because the interfaces between the two materials, they're not atomically smooth. It's better to actually diffuse in the dopants. All right, so what happens if we put donors and acceptors in this example? Nd is much greater than Na. So this is what happens. When you dope it, you're putting in, when you put in a donor, you get this donor level, and those donor states are initially occupied with electrons, but those electrons can go into the conduction band. When you put in Na, you get these acceptor states, and those acceptor states are at enough energy, electrons from the valence band can jump into those acceptor states and fill up those acceptor states, and it leaves holes in the valence band. But here, the key thing is, in this case, Nd is much larger than Na. The number of donors is much larger than the number of acceptors. So you're going to end up getting an N-type material. The way you can explain this with the energy band diagram is that you have a lot more dopants. You have many more electrons that are being put into the conduction band. And then some of those electrons are going to see these empty states in the valence band and come down and occupy them. And as a result, some of them will go away, but the fact that you have a much higher doping level on the donor side, you'll still end up with an N-type material. And in an N-type material, the Fermi level shifts up. So when you dope the material, I don't know if this is already obvious from what I told you, but when you dope the material N-type, what you're essentially doing is you're moving the Fermi level up in the material. When you dope a P-type, you're shifting the Fermi level down. So you as a designer control the location of EF. So we mentioned the simple case where like the donor density is much, much higher than the acceptor density, but what if they're actually close to each other? If they're close to each other, you have to use a space charge neutrality rule. For a material to remain electrostatically neutral, P0 plus Nd is equal to N0 plus Na. So where is that coming from? It comes from the positive and negative charges in the material. So P0, what charge does the P0 have? This is a whole concentration. This is positive charge. And what is Nd? Okay, so let's remind ourselves what Nd is. This is a column 5 element. And so let's say phosphorus. All right, phosphorus had that extra electron in there. and that extra electron is, it's going around and doing its thing. If you apply voltage to it, that electron will move around. It's free to move, right? So when the electron leaves this phosphorus atom, do you know what the effective charge on it is?
Positive.
It's effectively positive, right? Initially, when that electron was nearby,
Neutral.
it was neutral. But now that the electron left, it has that one extra proton in the nucleus, right? That's the difference between phosphorus and silicon. It has that one extra proton in the nucleus. So this ends up having a positive. This ion, they call these. The ion is positively charged. So this Nd has a positive charge associated with it, and similarly, this electron has a negative charge, and the acceptor ions also have a negative charge associated with it. So the boron in the lattice would have an effective negative charge. All right, so that space charge neutrality rule has to hold, and you can use that rule if I have a certain Nd and I have a certain Na. If you know what those two are, that can help you find P0 and N0. Okay, and I'll tell you another formulas that relate P0 and N0 together, so you could use those two equations to figure out. Here you have like one equation. If I give you Nd and Na, now you have one equation and you have two unknowns. P0 and N0 are still unknown. Okay, let me back up for a second. I saw some confused faces. So a typical problem that I would give you, a practical problem, is that you dope the semiconductor with a doping density of X. Your Na is equal to this many dopants per cubic centimeter. The donor density is this many dopants per cubic centimeter. What is the electron and hole concentration? So that's what your problem 3, your module 3 homeworks are going to be all about. Draw the Fermi diagram to find the concentrations of electrons and holes. So if I give you Nd and I give you Na, that's not enough to solve for P0 and N0. You actually need some more information, which we'll now talk about. But let's talk about a simpler problem, just to make sure that the intuition's in there. If I say the doping density, I'm only doping it, and there's no multiple dopant business here, just a single dopant, column 5 phosphorus, doped at a density of 10 to the 16th per centimeter cubed. So let's say, we'll do another example problem. Let's just say Nd is equal to 10 to the 16th per centimeter cubed. That means phosphorus dopant at 10 to the 16th per centimeter cubed. What is the electron concentration there?
10 to the 16th per centimeter cubed.
Exactly. N0 is equal to 10 to the 16th per centimeter cubed. And why is that, David?
Because you get one electron per phosphorus atom, and if that's the density.
One electron per phosphorus atom. That's right. As long as those electrons are ionized, one electron per phosphorus atom, which is what you can assume that at room temperature, that they will be ionized. Okay, and with multiple dopants, you can use this type of formula. Now, so far, we have like about a half an hour left here. So we're going to switch gears a little bit now. We've talked about how to calculate some carrier concentrations, and in your homeworks, you'll also be looking at how to draw the energy band diagrams. So the typical problem you're going to have in your homework is something like this. I give you a doping concentration. I say you dope at N-type at 10 to the 16th, let's say. What is the electron concentration? What is the hole concentration? And draw the energy band diagram showing the position of the Fermi level. Okay, that's one type of problem. The other type of problem is the reverse problem, where I say, I'm giving you the energy band diagram, I'm showing you the position of the Fermi level, tell me what the doping was, what type of dopants were used, and what the doping concentration was. but now we're going to switch gears for a minute, and we're going to look at some of the behavior of carriers. So we've talked about calculating carrier concentration. Now we're going to look at how they vary with temperature and doping. We're going to look at how carriers move in the presence of electromagnetic fields. So in that context, we'll talk about mobility, scattering, conductivity, and Ohm's law. So the first thing we'll look at is like how carrier concentrations vary with temperature and doping. So when you dope the semiconductor, what's interesting is that the product of carriers and holes remains constant. And this is a derivation of that. So let's say I dope the material N-type at a concentration of 10 to the 16th per centimeter cubed. I'm going to be upping my electron concentration, but I'm going to decrease my hole concentration, right? So as we saw from these diagrams, this is nicely illustrated here. So this is an intrinsic semiconductor. The electrons and holes are the same concentration of both. In an N-type material, you have a lot of electrons and few holes, and in a P-type material, vice versa. So what this next slide I'm going to talk about tells us is that the product of holes and electrons is a constant. That makes things a lot easier for our calculations. It's saying that if I doubled the electron concentration, then the hole concentration went down by half, by 50%. And the way that this, this can all be derived from fundamental principles. We're just going to do a very quick understanding here. So we first did this calculation. We said the concentration of electrons in the conduction band is equal to this formula. The concentration of holes in the valence band is equal to this formula. And this came from the density of states and the Fermi-Dirac function. So all you do here is you just mathematically multiply these two together, and let's see what you get. So you have NC times this factor EC minus EF over KT, and you have NV times exponential of EF minus EV over KT. So these are two exponentials. When you multiply two exponentials, what happens? What do you add? Yeah, e to the a times e to the b is e to the a plus b. So what you're doing is you're adding up EC minus EF and then EF minus EV. The EF term goes away and you're left with EC minus EV. Now what's EC minus EV?
Band gap.
The band gap of the material. It's a fundamental property of the material, right? So this EF part disappeared and you're just left with EC minus EV here. That's the key thing about this mathematical derivation. I mean, you guys can, this is just, you can do this yourself. I like to just point out the most important thing. So this EC minus EV is just equal to the band gap of a material. It's a fundamental material property for whatever semiconductor you're working with. In the case of silicon, is 1.12 electron volts. So this tells us is that the product of N and P is a constant for a given material at a given temperature. So Eg is the specific material and T is the specific temperature. Right, and that makes our a lot of our calculations much easier. So we go one step beyond that with those calculations, and we can say that if we want to figure out what's called the intrinsic carrier concentration, then we can figure it out this way. So let's just go through this real quick. The way that we define the intrinsic carrier concentration is that it's the carrier concentration at no doping. So and we know that at no doping, Ni is equal to Pi. I stands for intrinsic. The N and P are equal to each other. So if we do the same thing as we did on this previous slide, we multiply them together, Ni times Pi, we get this NCEV, the band gap over KT here, right? And so we're defining Ni times Pi is equal to Ni squared. And then when you take the square root of that, you get a formula for Ni. All right, so this whole formula just came out of the fact that the product of electrons and holes is constant. And so the intrinsic carrier concentration is a function of the band gap, it's a function of temperature, and it's a function of the effective density of states in the conduction and valence band. All right, just look at this formula and convince yourself that this makes sense. All right. The more states you have in the valence and conduction band, the more carrier concentration you're going to have. Right? You have more parking spaces, so you're going to have increase your carrier concentration. The band gap, notice that it's inversely proportional to the band gap. It's a negative exponential function of band gap. So it's a very significant function of band gap, exponentially related to band gap. As you increase the band gap, what happens to the carrier concentration, the intrinsic concentration? It decreases, right? The farther you are away from the Fermi level, the less chance there is of finding an electron or a hole. All right, and then you have this a temperature function too, which we'll talk about in the following slides. N times P equals Ni squared. Just remember this. Write this down. You're going to use this over and over again in your homeworks. Well, you don't need to write it down, but write it in your head. This formula is not used as frequently. This formula is used all the time in all your homework problems. Np equals Ni squared. And by the way, Ni for silicon is approximately equal to 1.5 times 10 to the 10 per centimeter cubed at 300 Kelvin. This is on a separate slide also, but just know that the Ni is a constant. So if you know what Ni is and you know what your N is, then you can figure out what your P is. So the typical way that you'd use this formula is that I say, okay, we dope the semiconductor N-type 10 to the 16th per centimeter cubed. So as David said, the electron concentration is equal to that same amount, 10 to the 16th per centimeter cubed. Ni is a constant at room temperature. And so from that formula, you can figure out your P concentration, your hole concentration. Yes?
Isn't that square root equal to 1 in the equation? Ni is equal to square root of NC. NC and NV are the densities, right?
Mm-hmm.
So NC density, or say suppose NV density will be equal to 1 minus NC, right? If it is intrinsic.
NC density is equal to 1 minus NV? No, this is the effective density of states, which is different from the Fermi function. Are you thinking of the Fermi function there?
No, I mean, even if it is. So that's a probability, right?
No, density of states is not a probability. The Fermi function is a probability. The density of states is how many parking spaces there are.
Right. So in that case, if NC is or the available spaces, NV would be the not available spaces, right?
No. And NV is just the sorry. NC is the number of available spaces in the conduction band. NV is the number of available spaces in the valence band. It says nothing about whether the states are full or not. Remember that an electron has to have a state to reside in. A hole also has to have a state to reside in. That's a key point. The absence of an electron, you have an empty state, that's a hole. If you don't have a state at all, that's not a hole. And you have to have a state and it has to be empty. So that's why it's not just 1 minus NV. All right, so simplified formulas for carrier concentration. So these are the formulas you're going to be using in your homework a lot. This N0 is equal to Ni times E to the EF minus EI over KT. The hole concentration is Ni E to the EI minus EF over KT. The reason why we use this is in practice, Ni will be given to us. Generally, for simple problems, you don't use NC and NV. It's easier to just deal with Ni. So if we start with the relations on these previous two slides, it's trivial to derive this N0 formula and P0 formula. So this formula gives you the electron and hole concentration as a function of the location of the Fermi level. So as I mentioned, one type of problem that you'll get is I give you the energy band diagram, which tells you the position of the Fermi level. You figure out the electron and hole concentrations. That's one type of problem. The other type of problem is I give you the electron and hole I give you the electron and hole concentration by saying like there's a certain doping density, and then you draw the Fermi the level. You draw the energy band diagram showing the position of the Fermi level, and then this is the form of the equation that you'd use there. These two are equivalent, obviously. You're just solving for EF minus EI there. Right? These formulas they'll all make sense. You're going to be using this over and over again in this class, so it'll become second nature to you. These are all units and constants to remember. I made a couple of these points before, but a lot of this, be careful about units when you're doing stuff in this class. You're going to find out that in some of the problems we use MKS units, and sometimes we use, instead of meters, we use centimeters. I wish that was never the case, but every field somehow sometimes finds its own units to use. So the units for length in this class is often going to be centimeters instead of meters. Also, the units for energy, sometimes electron volts are used, sometimes joules is used. For some of the early stuff, module 2, module 1, we use joules, and then going forward in the class, you're going to be using electron volts a lot. So just keep all that stuff in mind. The Boltzmann constant can be given to you in joules per Kelvin or electron volts per Kelvin, just like the Planck's constant has joule seconds or electron volt seconds. Q is equal to 1.6 times 10 to the negative 19 coulombs. That's the charge on a single electron or a single proton. Single proton is positive, single electron is negative. 1 electron volt is a unit of energy. It's a very small amount of energy, 1.6 times 10 to the negative 19 joules. Notice these two numbers are the same. You're gonna see this KT over Q very frequently. This is going to come up later in the modules. In this module, you're going to see this KT come up very frequently. You've already seen it in the Fermi-Dirac function. So wherever you have KT, KT is equal to 8.62 times 10 to the negative 5 electron volts per Kelvin. And if you multiply it by 300 Kelvin, meaning at room temperature, you're going to get 0.026 electron volts. So some of these numbers always comes up. This 0.026 number tends to come up whenever you have this Boltzmann constant times temperature. And then this 1.6 times 10 to the negative 19 also comes up when you're converting between joules and electron volts. And it also happens to be the fundamental unit of charge. So just keep that in mind. You'll remember this. It'll become secondhand when you start doing more problems. All right. Let's see, we want to get into so we can do a quick example here, I think. I would like for everyone to give this a go for the next few minutes. Just try it out. In the energy band diagram of silicon, suppose that the Fermi level is 0.3 electron volts above the intrinsic level. What is the electron and hole concentration? What is the doping? And what type of semiconductor is this? So the way you go about this, you draw your energy band diagram. This is your EC, and this is your EV. And so one point that this question makes is that it says the intrinsic level. Okay, I haven't told you what the intrinsic level is yet, but the intrinsic level is halfway between EC and EV. They call that the intrinsic level because if the Fermi level is positioned at the intrinsic level, that means it's an intrinsic semiconductor. So right now it's saying that EF is 0.3 electron volts above the intrinsic level. So let's just get our bearings here. This is 1.12 electron volts for silicon. All right, so this is about 0.6, this is about 0.3. I'm just putting it here. So the Fermi level is positioned just 0.3 electron volts above EI. So from this position of this drawing of the Fermi level, you should be able to figure out what the electron hole concentration is. And in the interest of time, I think I can just go ahead and show you that. I think we can just cram it in here on the same slide. So this is the one that you want to use here. If you want to figure out the electron concentration, you can also use this to figure out the hole concentration, but I'll show you how to use this one and then also use NP equals Ni squared. So EF minus EI is KT ln of N over Ni. All right, so, or actually, I'm sorry, this is the this is the one we want. Sorry, this N0 is equal to Ni EF minus EI over KT. So the electron concentration N0 is equal to Ni exponential of EF minus EI over KT. Just want you to see how simple these calculations are with these types of formulas. So Ni is equal to 1.5 times 10 to the 10 per centimeter cubed. All right. Remember, the units for this is 1 over centimeter cubed, and the units for this is unitless. It has no units. All right, so the exponential here, exponential turns out to be, so we have 0.3 electron volts. And from the previous slide, this is why I brought up the units and constants on the previous slide, that KT term, the KT term is equal to 0.026 electron volts. All right, it's a very simple calculation here. So 0.3 divided by 0.026. Let's see. If anyone has a calculator handy, try it. Let's see if mine is working. Let's see here. All right, so 0.3 divided by 0.026, that's about 11. Okay, this ratio is very important because it's an exponential term, right? So this second term in the equation is going to go up very rapidly the higher that ratio is. The EF minus EI divided by 0.026. The ratio of those two numbers, EF minus EI and 0.26, is going to be the term that causes the exponential to rise very largely. And when this exponential term gets larger, then this you multiply this Ni by a larger and larger number. So if I do the exponential of, let's see, exponential of 11, sorry, 0.3 divided by 0.026. I get 1.02 times 10 to the 5th. So this is 1.5 times 10 to the 10 per centimeter cubed multiplied by 1.03 times 10 to the 5th. Oops, I'm going to do that. And so our electron concentration is approximately 1.5 times 10 to the 15th per centimeter cubed. So there's our electron concentration. And to find the hole concentration, we just use NP equals Ni squared. So the whole concentration is going to be Ni squared over N. So this is 1.5 times 10 to the 10 squared divided by 1.5 times 10 to the 15th. Do that real quick. 1.5 times 10 to the 5th, right. 1.5 times 10 to the 5th per centimeter cubed. Okay? So you got your whole concentration and electron and hole concentration here. So this is your P0. Oops. This is your N0. And what type of semiconductor is this? What's that? It's an N-type, right? Why is it N-type?
More electrons.
There's more electrons than holes, right? You can also say the Fermi level is positioned above the intrinsic level, so it's N-type. More electrons than holes, also a valid answer. So the other thing I want you to notice in terms of numbers, the intrinsic electron level, the intrinsic level is 1.5 times 10 to the 10, right? So if you don't do doping, if you had no doping at all, the electron and hole concentration are both 1.5 times 10 to the 10. By doping it, what I did is I increased the electron concentration by more than 5 orders of magnitude. Now it's 1.5 times 10 to the 15th. The hole concentration went down by the same amount. It went down by 5 orders of magnitude. Right? So as the electron concentration goes up, the hole concentration goes down. Just keep that in mind. The product of the two is always a constant. It's one of those intuitions that's just like becomes second nature to someone working with semiconductors. It's like if you hit the ball with the bat, the ball will go faster. It's like that. You increase the electron concentration, the hole concentration goes down.
So the Ni value given there was a constant for silicon.
I'm sorry?
The Ni value.
Yes.
Is it a constant for silicon?
It's a constant for silicon at room temperature. Yeah. So this formula for Ni, keep this in mind, is that it is a function of, it's a function of, it's an exponentially a function of temperature. All right. So in the last 5 minutes here, what we're going to do is we're going to go over the temperature dependence of an extrinsic semiconductor. So what we're doing here is we are looking at this curve. N0 versus temperature. All right, and the thing to keep in mind here is this is 1,000 divided by temperature. So this can be a little bit confusing. You're going to higher temperatures as you go to the left. So this is low temperature on the right, and then as you go to the left, the temperature is increasing. So temperature on the x-axis, y-axis is the electron concentration. So what's happening here, this is the temperature dependence in an extrinsic semiconductor. So there are 3 zones here, the ionization, the extrinsic, and the intrinsic. And I want you to understand what's happening in each one of the zones. This is actually a good review for concepts that we've covered already. At very low temperatures, this is what you have. At very low temperatures, you have an N-type semiconductor. All right, keep in mind, this is N-type silicon doped with 10 to the 15th column 5 elements, phosphorus. So this is what your energy band diagram looks like at 0 Kelvin. You have the donor level, and those donor levels are occupied by electrons. At 0 Kelvin, there's not enough energy for these electrons to go into the conduction band. So that is why the electron concentration drops at very, very low temperatures. At moderate temperatures, there's enough temperature for the electrons in the donor level to go into the conduction band. All right, and it doesn't take much temperature to do that. So 50 Kelvin is all it takes to get these electrons to go into the conduction band. So from 50 Kelvin onwards, so 50 Kelvin is right about here where my mouse is. From 50 Kelvin onwards, you have basically a fixed electron concentration. All right, this is the electron concentration that we generally talk about in our problems. If you dope it with 10 to the 15th, if you dope with 10 to the 15th of phosphorus, you're going to get 1 electron for every phosphorus dopant that you put in there, and so your electron concentration is 10 to the 15th. This is called the extrinsic region. But once you get to super high temperatures, now you have enough temperature where electrons in the valence band can also jump up into the conduction band. Not just the electrons that were at the dopant level, now you have electrons in the valence band getting up to the conduction band. This happens at very high temperatures. And so this is the zone which is referred to as the intrinsic zone, and this is where the doped semiconductor actually starts to behave like an intrinsic one at the same temperature. All right, so that's the temperature dependence in an extrinsic semiconductor. We talked about the temperature dependence in an intrinsic semiconductor. It looked something like this. It was just that, let's go up here. It looked like this, if you all recall. It was just this exponential function, just a straight line. When you plot it in a log scale. And for an extrinsic semiconductor, the temperature dependence of carrier concentration is a little bit more complex. There's the ionization zone, the extrinsic zone, and then finally the intrinsic zone. All right, so that's a stopping point for today. What we'll do next time is we're going to start to talk about electrical currents. So revisiting circuits 1, and then revisiting electromagnetics, where we start taking a closer look at drift current. We say, okay, we're putting a voltage over a semiconductor material. We get an electric field, and there's electrons and holes, and then there's those electrons start to move when you apply a voltage to it, and so the speed is due to the electric field and mobility, and then you can calculate current density, and eventually you can calculate the current. The reason we use these formulas is ultimately we want to get at an equation for the conductivity of a material. We want to get at an equation for the resistance of a semiconductor material. So a semiconductor resistor is the first basic semiconductor device that we look at in this class. We look at diodes, BJTs, and MOSFETs later, but the most basic type of component, the semiconductor component, is just a resistor. So we'll figure out how to calculate the resistance of a doped versus an undoped semiconductor. I'll post the homeworks by Wednesday as well, so you can get started on that. If you haven't had a chance to look at the homework solutions for this one, please do so, because otherwise it's going to be hard to keep up in the class. There's a lot of materials, so go for it. Yep.
For the test,
Mm-hmm.
do you allow a cheat sheet or something?
Yeah, for exams, I allow you 1 page of notes front and back, not photocopies. 1 page of notes front and back for the midterms, 2 pages of notes front and back for the final.
How big?
Just a regular 8.5 by 11. Yeah. You're right. I never specified how big. You could bring in like a toilet paper roll full of.
Do you know when the first exam will be?
Yeah. So the first exam is going to be scheduled for. I just went over that last week.